Okay, well, we'll kick it off here and get started. This is being recorded as well, so you should be able to go back later if you're interested in watching it. And I think it's actually being live streamed, I hope. That would be great. I'm Chris Brooks. I'm a research fellow at the University of Michigan. You've met Zach Pardos from UC Berkeley and Srecko and Vitomir from Fraser University. And the goal that we put together for this workshop was really to try and help educational researchers who might not have a strong theoretical computer science background understand how they might be able to use some of the data mining tools with their data. I'm going to skip, because we're running already, just because of the way the rooms were set up, I'm going to skip this quick around the room and hopefully later to chat about that anyway. The focus here is on practical, hands-on usage of a Weka toolkit. Weka is a toolkit that was created out of Waikato in, I'm probably saying that wrong, New Zealand. It's a great toolkit, it's very accessible, it's totally free and open source. And hopefully you've already downloaded that from the first slide. We're not going to go into great depth on data mining theory, but we could go into more depth if people are interested. My preference would be to do that tonight over drinks, or tomorrow over drinks, or the next day over drinks, because I want to make sure everybody gets something out of the tutorial. But if you want to dig in a little bit more, we've all used different methods and different toolkits, and so I'm sure we'd happily talk to them about that. I'm going to introduce two really well-known methods. One's called K-means clustering, the other is J48 decision trees. And then I kind of wrote down here, what about a casual post-tutorial chat and hack throughout the week? So I don't know what the rest of the week schedule looks like, but if there is an appropriate kind of downtime where there's an hour, maybe in the evening tomorrow, or after the end of the conference tomorrow, if there were people who are interested in getting together a kind of birds of a feather to talk about their educational data sets and how they might start data mining those, maybe you've even got some of them with you that we could look at and kind of share experiences with or poke around, then I would be happy to do that. So maybe the way to organize something like that would be just to hit Twitter and just start seeing if there's a bunch of people who are interested in a kind of birds of a feather on data mining educational data sets. Some other resources, again, these, as Eric mentioned, these slides are available. They will be available on the website, or if they're not already, but they're also available in that first link to the data sets, so you can kind of grab them from there if you need to. There's some other resources, though, that are excellent. This is the book that accompanies Weka and was written by some of the creators of Weka. It's an excellent book. There's also a MOOC about it, and now there's been a second MOOC about it. And it's very accessible and very understandable, I think. So there's a link there, and I think it's just a wonderful resource. Also, Ryan Baker is here, as you've no doubt realized from this morning, and he taught a MOOC on Coursera last fall that I think was excellent. It's much more complex than the Weka MOOC, but it dives into a lot more of the theory and some of the nuance and some of the other measures that I think and methods that I think are really interesting. And so here's the URL for it. He's actually now decided to make that a kind of open access textbook, so you can do whatever you want within some confines of the license with that textbook. An excellent resource. You saw all the discussion today about LAMP and the master's program that's kind of being created, so I think that'll be stellar as well. So the first topic I would like to introduce is clustering. And the question is we're trying to answer when we think of clustering is how can we use data mining to better understand the relationships that exist within our data? And what techniques can we use when our data is too big to understand at a glance? So sometimes you have this educational data, like who completed what assignment and what grades they were given and so forth. And you can kind of put it out on spreadsheets or lay it out in front of you and get some intuitions about the relationships that exist. But what do you do when there's more than 10 students, when there's 20, 50, 100, 1,000, 100,000 students? When you're looking across school systems, when you're looking across disciplines, even just across sections, and you get a little overwhelmed by the data. So what kind of techniques can you use? Clustering is definitely one of these. What do we do when we don't have an educational theory to guide us deeply in our investigation? So you can take some educational theories, that are very broad and say make a few impactful things like social constructivism, for instance. This is a nice educational theory, but how do you operationalize social constructivism? I think it can be very difficult. So if you don't have a very specific theory, like Anderson's ACT-R, for instance, that you're looking at in the context of your learning system, what are some of the techniques that you can use? I think clustering is a good one to start with. And when another reason we could use this is when we don't know how to map our data onto educational theory. So we have all of this activity data in a content management system, or in an item response system, like a clicker type system. And we just don't know how we're going to tie this across into our educational theory. So in a nutshell, clustering is the grouping of like instances based on their properties. And this is generally done in an unsupervised manner, so this is automatic. This is not used as a person having to do much, except you then label, you interpret the results of the clustering. And so it just says, hey, there's these little groups of people that are similar to one another, but it doesn't say, and these are social constructivists. These are, these are all men who come from first-generation families, and that has a special label or something like that. That's something that you, as the educational researcher, need to impart into it. K-means is a very simple and often used method. I think it's quite effective to get an initial glance of your data. There's certainly more sophisticated methods. If you consider a list of students in a two-feature space, like GPA versus age, the goal is to find the best K, the best number of clusters, or sorry, the best fitting clusters in this data. So you set, oh, I think there's going to be 3 clusters in my data. My educational theory tells me there's kind of 4 groups, and then we look at this two-space of GPA and age, and we want to see where those groups are. This helps us answer questions like, are there interesting groups? How many students are in groups compared to one another, which is also, I think, often quite interesting, and how well do students actually fit into these groups. And so a group is really defined by a centroid or a prototype. So this is a form of prototypical reasoning versus ontological reasoning, and we can kind of talk more about that if people are interested in what those what that means, kind of from a computational perspective. But what it means is there's a stereotype, there's an example, there's somebody at the middle that represents what this group is, and how well do the people in that group fit that stereotype? How well do they fit in? So it's important that we're not losing that nuance. What we're gaining is a new nuance of what that stereotype might look like. In educational clustering, models are usually descriptive models to help understand the interplay of data and theory. They're not necessarily predictive modeling. So if you're looking for early alert system and predictive modeling, that's part 2 after the coffee break when we talk about J48 trees. This is more descriptive. Okay, so the algorithm is fairly simple. You set K equal to the number of clusters. For instance, K equals 3. You randomly assign values to these 3 clusters. So you just put some dots in this 2 space of GPA and age. You just put some points out there. You assign the data points to the closest point. You calculate the center of that circle that's created, and that's your new centroid, and then you just repeat. And you keep doing that until you achieve some form of stability. So I can show you that, or I can actually show you it being done. And this is a great example. That was pretty gutsy, hey? I didn't even check to see that my wireless was on. All right, so here's a wonderful example of how k-means is done. So here we've got 100 people in our 2 space of GPA and grade or GPA and age. And this is just a 2 space for visualization, but actually you could have any number of features. So you could have demographic, you could have GPA, you could have age, you could have level of knowledge, answers to Likert questions coming in, etc., and be trying to find clusters. There's 3 random points. So here's one, this little green point here. Sorry, 5 random points in this one. There's a green point here, purple here, blue here, yellow, and red here. And the algorithm just says assign all the white points to the nearest colored point and color them. And so that's what that looks like. And so that's our initial clustering. And then we just keep doing that. And so we keep calculating the center of each of these groups and reassigning the colored points until we hit some kind of stability. And you see that stability, it may take a while to happen. Sometimes never happens. And then this is kind of the result. And so this is the goal of k-means, is to then come back to you and say, here's this centroid, this centroid, this centroid, this centroid, and this centroid. Those are prototypes of students that fit, that represent those clusters. But it's not saying that these people are those centroids. It's saying that these people best fit or best resemble those centroids given all the other centroids. Choosing the number of k is important. Choosing the number of k is important, and that's your job to do as a researcher. And there's some challenges in that. Okay, so the pros of this approach, it's actually fast enough for fairly complex data sets. Not in the big data particle physics view of the world, but more in the big data education view of the world. And it's fairly easy to interpret. Hopefully from that example, it's fairly clear what these prototypes mean and how you might find them. The cons, it's pretty sensitive to the initial values that you've chosen for k equals 1, 2, 3. Generally, you actually do this k-means clustering, let's say with k equals 4, and you do that 1,000 times and take the best value because of that sensitivity to those initial clusters. And it's actually not clear always how to choose that initial k. And there's 4 different techniques that you can use to choose that k. Intuition, I would say this is probably the most frequently used technique, but maybe not the most principled. Experimentation, you can try different levels of k. Now, as k approaches the number of points in your data set, you get total overfitting. And this I actually really like this because everybody is their own kind of unique flower in the garden, right? We're all individuals. And so this is exactly what it means, right? If k equals 100 and you've got 100 people, well, unless 2 people are identical, everybody's going to be in their own cluster of 1. So it really forces you to think about what you're trying to form a prototype around. There's also pedagogical theory. If a particular theory says there's 4 kinds of people in discussion forums, and then you have all of these different features that describe discussion forums, and you say k equals 4, and you get those clusters back, they may align with your pedagogical theory if the features are representative of aspects of the theory, and the theory is correct, which is a really exciting thing because now you have a way to kind of empirically verify and describe alternatives. What if k was equal to 5? What if k was equal to 3? And how does that fit with the theory, and what kind of is the level of error in those clusters? And there's also a method called the elbow. And so the elbow is a method that some people use. You shouldn't over-rely on this method, but it's kind of an analytic method, and a lot of people like it. So you calculate how well people fit within their centroid, so that's Euclidean distance, just the distance the people are from the center of that prototype. And then you essentially graph it, and you look at the average error divided by the set of the individuals, and you look for an inflection point in that graph. And you can just use Excel, or Weka might even have built-in support for that. You look for an inflection point, and this is kind of the idea that you're reaching a case of diminishing returns. That as your number of clusters are getting bigger, you're not contextualizing more and more people. That seems to be a natural fit. Again, the elbow is not something to over-rely on, but it's kind of a neat thing to do. All right, so there's 2 synthetic data sets that I've created. They're based on some kind of real data sets, or they've got some dimensionality reduction that's been done to them to make them a little bit more tractable. And I'd like you to pull those up. So if you haven't downloaded them, oh, the link's right down there. Look at that. Can anybody actually read that? It says bit.ly/LAC14, which is not today, but was months ago, --tutorial. So if you haven't grabbed those data sets, please grab them from there. Inside of those data sets, if you open them up as a CSV, you'll see it's data across here. It's essentially for different weeks of the course, so week 1, week 2, week 3, week 4, week 5, etc. for different students, and those are, each student gets their own row. Did they watch lectures from a lecture capture system, or did they not watch lectures from the lecture capture system? And so the goal here was, what are the clusters of viewing activity by the students?
Chris, there's more than one CSV file.
Yes, I would like you, there should be one called 15 and one called 8, I think. Does that sound right? Yeah, so we'll start with 15, I guess.
There are two.
15 underscore cluster, we'll start with. All right, so then fire up Weka, and we'll actually do some hands-on.
If you have any problems with this installing,
Yeah, if you have challenges, just toss your hand up. And we'll fire up Weka and start here. So this is actually what a Weka is, this little bird up here. Looks kind of like a dodo bird, but it's not, it's a Weka. And I guess it's a native New Zealand bird. So we're going to do some exploration first. And so we'll just choose the Explorer, and it should open up a UI that looks like this. There. Some of the top is getting cut off here. Hopefully that this is readable and useful. And let's open, you'll have to change it down, I think, to CSV files. And 15 clustering. Does that look good? People are still with me? Okay. So Weka tells you kind of a couple of things. And this will be easier if I come here. It tells you a couple of things about the data set. First, it tells you the different attributes that are in the data set. So we have week 0, week 1, week 2, etc., all the way through. These are just different columns. It tells you how many instances there are. So here we're looking at data for 259 students. And then when you have a particular value selected, it will tell you what the labels are, so what the data values are, and what the distribution is. And it shows you a nice picture here. So for week 0, 255 people didn't watch the lecture, and 4 did watch the lecture. That sounds about right.
Is this synthetic data or real data?
It's synthetic, but it's pretty typical. I just did some dimensionality reduction. And so you can see as we look through, oh, look, that increases, and wow, all of a sudden there's a couple of weeks with big watching. This was, what did Pierre say when the professor falls on the stage? These are the big weeks. Okay. So there's different kinds of data types that you can have. We're all used to numbers, real values that range between minus whatever to plus whatever. But we can also have categorical values. And because this data set had strings, not watched or watched in the CSV file, Weka automatically determined that these are categorical values. And it does this, and it tells you right up here what the data type for a given column is. So this will be important more later on. I tried to set this one up so that we'll step into this. So these are categorical values. Is there a question? No, sorry. Okay, so we're going to click on the clustering tab, and we're going to jump into clustering. Now, there's lots of different methods for clustering. EM clustering is very popular. So and then simple k-means. Now there's a whole bunch of configurations that you can give to k-means. And there's one that we have to give. 2 points to anybody who can guess what we have to give it. K, thank you. The value of k. How many clusters we actually want. You keep score. 2 points up. So it's a little unintuitive. You actually have to click on the label here to configure the cluster, which is a little unfortunate. But there's a couple of other things that we can give it. We can ask it to display standard deviation, so to give you that information. We can tell it to use a different distance function. Generally, you start with Euclidean, but let's say you've got log transforms and you want to change that to Manhattan distance or whatever, you could do that. It could deal with missing values. This is the one magic one here, max iterations. So that's how many times we're actually going to run k-means with randomized starting points. And number of clusters here, and then a seed. Now the seed value is kind of neat. It basically means that it's going to run randomized, but it's going to seed the random engine with that value. So it means if you run 500 iterations with a seed value of 10, you'll get the same result every time. If you change the seed value, you'll get a different result. And this is cool because as a researcher, it allows you to try a couple of different situations and be able to go back to them, share them with colleagues, and be sure that you've done a randomized run, but you're actually have a replicable result that other people can share. So, yeah, I think we can use these in different ways. Let's just try 5 clusters. So I've got cheat sheets up here, right? That tell me what might be interesting versus what won't be interesting. And then OK. OK, there's some things about test sets and training sets. We're going to ignore those right now, and we're just going to hit start. OK, so hopefully it ran relatively quickly. When you run it, this little bird down here gets up and does a little dance. It's kind of neat. It tells you that it's not broken. As your laptop grows in expense, the bird dances less. So there's definitely, you have some options there. So the things I want to point out here is note the error measurement, the number of iterations that were run before stability, and how to read this. So, probably have to scroll down. So these are the 5 clusters that were found, 0 through 4. There will always be 5 because you're told that there are 5. Actually, if there's only 4 different kinds of, actual instances of data, you might only find 4. I'm not sure. I've never done that. But yeah, so these are the 5 different clusters that I found. And this is the distribution of the number of people in each cluster. So we see one cluster is made up of more than half the people. 51% of the people best fit one particular cluster. And then the rest are split between these 4 different clusters, clusters 0 through 4. Your results should be the same as mine unless you change the seed value, in which case they may be different. It tells you how many iterations were run before stability was achieved. So even though we told it it could run up to 500, it only had to run 4. So that's nice and gives you an idea. It gives you a sum of squared error across the different clusters. So this is nice because if you get some value, you can compare it to other people's to get an idea as to how well people actually fit within those clusters. And then here's the actual data of the cluster itself. So here it'll tell you for this cluster, let's say cluster 0. Well, let's look at cluster 2. It's quite nice here. So here at week 1, generally people did not watch. They did not watch in week 0, 1, 2, 3, 4, 5, 6, 7, 8. In week 9, they tended to watch. 10, 11, no. So what's going on? This is a pretty big cluster with 50. It's not the biggest, but what's going, what would we kind of look at theoretically as far as a construct? What's maybe happening there?
Uses were tended, so this isn't, they don't all match this, it's just that they tend to go towards.
That's right. That's very important, in fact. This is what the prototypical student looks like. That's the center. There will be people in that cluster that maybe also, they watched week 13 and week 9, and so they best fit that cluster versus the other clusters, but they're not perfectly in that cluster. That's very important with clustering. This is not 50 students who did this. This is 50 students who most closely did this, given the 5 different clusters discovered. So if you were an instructor and this was your class, what do you think is happening here?
There's a midterm.
Yeah. So this is the week of the midterm, and so we published some research. We showed exactly that. This is actually, I think, the second largest cluster, and we had different names for them. I think we published with the just-in-time is how we labeled that cluster. I think in our previous work we called it the oh shit cluster. The midterm is here and I have to learn something, and so I'm just going to cram like crazy in this one particular week. We see that there's other clusters. Here's one where it's 3 not watched, then a whole bunch of watched, then 4 not watched. So that's interesting as well, right? The beginning of the course maybe isn't so interesting. I haven't revved up and I don't feel like I regularly have to watch. Again, as Eric mentioned, some people in this cluster did watch in that first week. They just best fit this cluster. But then I've regularly integrated watching of lecture material through video into my study habits, and then the final exam period comes, and that regular watching isn't something that I continue with. So this actually was another cluster. It was actually in some of the research we did in this was actually a fairly small cluster, but these students came in with the same grade point average, a not statistically significant different grade point average coming in, so they had relatively the same marks, and left with a statistically significant different grade average going out. And the mean difference was 15 points actually on a 100-point scale. So people that gave us suggested that there's a high correlation between watching regularly and attaining a better mark than expected given your incoming grade point average.
So in this column that says full data, all of them are not watched.
Yeah.
However, when you were browsing through the data, there were weeks in which there were more watched than no watched. More students watching the lecture than not watching it.
Yeah.
So full data means if all the data is one cluster, how would you categorize all students? It's like one cluster solution. You have only one cluster for the whole data. That's described not watching at all. As you put more clusters into story, 5 in this case, you see the smaller differences. That's it. Basically, always, no matter how you change K, the first column is going to be the same. It always gives you one cluster solution.
So the question is though, why when we went on the first tab, on this processing tab, when we look at the graph that's created down here, why isn't the full data just a bigger bar all of the time?
So we cannot watch.
Yeah, like if we go down to different weeks, if you could please.
Yeah. No, I'm with it. There we go.
Like for example, week 4, more people watch than didn't.
Oh no, it flipped the labels.
Yeah,
that's wonderful.
Yeah,
so because it creates the labels in the order that it finds them in the data. So here it's actually, so I was also, as you were saying this, I'm like, holy crap, I don't have an answer for this. But actually it's just that here the data, not watched is a 1 and watched is a 2. But if you go down, you just flip them. So actually
it's always non-watched. Please go, non-watch is always bigger, right?
Yeah, that should be. Whew. I thought I was going to have to do some serious pedaling there.
I'm sorry.
Yeah.
I mean, maybe you talked about this before, and I missed it, but in terms of the outliers, is there anything in here that kind of summarizes the outliers?
No. So outliers. Yeah. So outliers. Well, so that would be the standard deviations actually. So you can include when you click on this. You can include whether you want to display the standard deviations. And that would contextualize what that outlier space looks like. But there's otherwise no easy way to do it. Now, all of the Weka libraries you can call programmatically from the API as well, and you can actually get the full results of what was created. But it's fairly easy to do that in Excel, too, for yourself, once you're given the actual centroids of the clusters. Because then you could go back, if you use Excel, many people do, if you go back to something like that, a spreadsheet program, to determine who's actually in which cluster. But just that standard deviation, I think, is the best way. What I often do is kind of create for each of these clusters, I determine how much error there are in each of the clusters. Because in some clusters, there's actually very little error. And one of those would probably be this one over here. The very last cluster, which we also found in our data to be the biggest cluster and have the least amount of error, were people who never used the system at all, because they presumably have other methods of consuming content.
So error in that sense, in that case, it would mean the misclassification error? Or are you talking?
Yeah, let's call it the distance they are from the prototype. Somewhere. It is error, but yeah, it's not a classification problem. So it's a clustering one. So we're finding these points that best represent the groups. So the error in this case is how far they are, how well they fit into that cluster.
So then does that come with the model fit evaluation as well? Or?
Yes, there are various ways of doing that. So as you can explore kind of the different. What do I want to show?
Visualize maybe what?
I can't remember. I've never found the visual. I can't talk. Keep closing the window. I've never found this visualizer useful. But you can do. I don't remember where it is, but you can do more sophisticated analyses of how well the models fit and what the error is.
Can I chime in here?
Yeah, please.
I think Chris isn't showing because it doesn't come in WECA, so it's not a practical suggestion. But there is a quantitative way of measuring the fit of clusters, which is called silhouette method, which is how tightly clustered they are. If you have a class that's with your data set and you want to see how well your clusters match that class, there's something called the Hungarian method, which tells you how close a correspondence your clusters are to some class. But it really isn't usually a classification problem. In fact, it's the opposite of that in machine learning. It's unsupervised machine learning, right? Where there's no label. So we never know if we have the ground truth real cluster label that we've identified. It's all unsupervised.
Yeah, please.
Yeah, and that's for this case. There is some use to you. There is some measures like the entropy. So you don't know the classes, but you want to know how the points in the class, in the cluster itself is homogeneous. So you calculate the entropy for each cluster, and the lower the better. The lower the value for the entropy, the better that these points in each cluster are homogeneous.
Right. So usually then you will want to start with the lowest cluster that means the minimum, which is 2, let's say. And then you will want to compare the model fit actually by comparing entropy values and EICs and residual values, right? So whether or not the
there's different ways to do it. You can also do this elbow method as well, which is trying to get at the same thing, and how well does it fit, and looking for when your accuracy versus is dramatically changing versus how much you're able to distinguish the data. So let's look at a couple of other ways to slice this. So you can change your number of clusters. So for fun, we'll just do 2 clusters. So essentially what we've asked is, let's put all the people who generally don't watch in one category. What would the prototype of the next category of student look like? And so they would have a bunch of watched with a couple of weeks not watched. I think that's kind of interesting from a pedagogy and reflective. Remember, this is kind of an explorative situation with clustering. So I think that's kind of interesting from a pedagogy perspective. What is it about these couple of weeks of the term or the semester that lots of people were not watching? In general, everybody best fits that a category if we only have 2 categories where there's some not watching going on. Or what's interesting about week 4 where people are regularly watching. And so you can kind of explore this as an instructor. Or as an instructional designer. And also it's interesting to see kind of what the sizes of the clusters would look like. So if we were just going to have 2 clusters, how many people would fit into this generally don't watch ever versus how many people would fit into the other cluster being created. We can open, there was a second clustering data file, I believe. 8. I'll just open it in Excel. Hopefully I'll open it in Excel. So this is just what the data file looks like. You can see how wonderfully readable it is. So the first is just the list of all of the different features. So I have week 0 through week 18. And then for one particular student, did they watch or not watch? So here they not watch, not watch, not watch. Here they watched, here they not watched, and so forth. So I hope it's fairly straightforward how you might be able to put your data into something like this, depending on the kind of data that you have, and how straightforward it is actually to start doing a little bit of a cluster analysis. So this is a similar data set. It's actually, so I took 2 real data sets and I modified them with some dimensionality reduction and some obfuscation and so forth. But this is actually for a different class. When we did some research, we were looking specifically at STEM classes. I don't remember if these are both STEM classes. If we want to cluster and so here, if we look at the results of clustering for this class of data, we have these 2 classes are kind of interesting. We'll just maybe skip those for a minute. But we have this big not watched group of people. So that's common, and that's across all of our data. Go figure. And that's, a lot of students who watch it. But then what's also pretty common are people who fairly rigorously integrated into their learning method here. But then actually this course has 2 midterm exams. And so a bunch of people watched during the first midterm and a bunch only watched during the second midterm. And this was kind of a neat result to find that there were people who are, very early on, they're like, oh, this technology is going to help me learn. So this is, of course, our learning hypothesis now after seeing this data. Oh, this technology is really going to help me learn. So I want to, get on board. They watch early during the midterm. They're like, that was useless. I'm not going to do that. Or I'm dropping the class, or kind of whatever. And then we have a little further down, we have people who skipped it the first time around and for the first midterm, and they're like, okay, I've got to bring up my grades, I've got to bring up my average, and I'm going to kind of watch here. And then what happened to them? We're not really sure. They didn't integrate it into their learning. So this is interesting because then you can say, take that, the data drives actually the hypothesis generation, and then you can start doing things like maybe have a survey or have small group meetings with some of the students in these clusters to try and understand what was going on with them. You don't have to, survey all 250 students. You can just grab these 50 students and say, hey, there looks like there's something interesting with just these students, and kind of form the next hypothesis. If you think that this is a common method of doing things, then you can try and replicate the results the following year or in other courses. And so just as part of our original research on this, we ended up building a model for STEM courses that said there are kind of 4 or 5 interesting clusters in a STEM course, and then we replicated that in multiple years and showed that the error rate for those clusters didn't really change, or didn't change significantly for other STEM courses. Now, we didn't do it across all STEM disciplines. We just did 2 chemistry classes and then a biomolecules. So 1 chemistry class, then the exact same class the next year to do a replication, and then a biomolecules, which we figured was similar but different at the same time.
Yeah, just I wonder if you can go the other way. Kind of, let's say I had some theory and I wanted to kind of define my own prototype in this, and I can see on the one hand I don't want to say, well, just look for this, but I might want to say, well, how many clusters do I need for this to be a legitimate cluster, or something like that? I mean, is there a way to go about that? I'm thinking in a more dimensional space that might be common.
Yeah, there's not a in Weka, there's not like a technological way of doing that that I know of. Doesn't mean that it doesn't exist. Because you can generate models from within Weka, save those models, and then apply them to new data. So what I did for this was I would write Python scripts essentially with the centroid of what I was expecting to see. Because in some ways this was part of my replication, right? In the next year, I didn't say, give me the best 4 clusters or 5 clusters. I said, here are the prototypes, now show me what the error is in each of these clusters. And I looked at how much that error differed, and then, you know, then it comes down to arguing how well the difference fits. We did apply this approach in a first-year course as well. A first-year STEM course was totally different. The models did not fit well at all. So I don't know that Weka as a tool has some opportunity there as much as, in general.
Did you say that in this tool you can see the model fit in the errors by cluster, or is it all that you get is the within cluster substrate?
You only get the within cluster, yeah, unfortunately.
So what is the benefit of doing this over, using Python or SPSS or SAS and you came into cluster models?
Oh yeah, no, if you've got Python skills, I would use a lot of Python skills. I do a lot of, so this is straightforward, easy load of CSV and click away, don't write any code. But definitely I think that if you've got Python programming background or R programming background, then more sophisticated methods very quickly are going to be interesting.
One other thing, you can use Weka as a library. So in Java, it's written in Java, so you have your Java code, you just load this in a .jar file, you just call directly class called k-mean something, you load, you give it the data and so on, so you can use it as a library as well. Actually, I was using it like that. Never.
So the way I typically use Weka is I click around a little bit to kind of explore the data and get an idea as to what the shape of the data might look like. But actually, if you look up here, it tells you exactly what class file you need to call, and you can call it through command line. So I do all my Pythoning, and I just script it all up and just do sub-process calls and eat the results. So I use Weka to as a library, or not even as a library, but as a command line program to find out my cluster centroids, and then I just compare those. But you can, with Python, you have a lot of you have like scikit-learn and kind of a lot of different clustering tools that you can use, I think, as well. Zach, did you have any thoughts on that?
I mean, with Chris on this, my tool choice is MATLAB. MATLAB has powerful k-means tools. It has another kind of increasingly popular clustering tool called Spectral Clustering, which is instead of clustering assuming spherical Gaussians, or instead of assuming that your users, in this case, their attributes are clustered in clumps, instead it assumes that perhaps they're clustered in a way where they all connect to one another. Let's say a radial distribution where you have a radius of connections. K-means will not be able to capture that radius or that ring, whereas there's different kind of clustering methods that can capture that kind of connectedness, and I'll touch on that briefly in the second part of the workshop.
So just before, just to follow up on what Zach said, the Wikipedia page actually for clustering is really interesting because they show lots of great examples that break specific algorithms or methods, horseshoe shapes of clusters, and things that you and I might look at and say, there's clearly a relationship of some kind, this geographical relationship, geometrical relationship, but k-means just breaks because it's looking for round globs and things. And you can manipulate a little bit of that by changing your distance metric or tweaking with the data on pre-processing, but as you get into more and more clustering, there's a lot more interesting techniques. You can think of clustering as counting the number of peaks on a mountain and trying to look at how many peaks there are on a mountain. Then the question is, doesn't every boulder that sits on top of, in a mountainscape somewhere, isn't that a local peak? And the answer is, well, yes, kind of. And so you've got these jutty mountains with little pebbles, or mounds of pebbles that are their own local clusters as well. And so how do you end up kind of characterizing that? And so there's a whole bunch of different mechanisms for trying to count those.
So if I understood well, if you have 10 people at each week, K-means won't find a cluster, meaning I just watched one week.
Sorry, if you have 10, what's the
10 the first week you have 10 people, and then at the second 10 people, and then watching the videos. With K-means, you won't find that there is a cluster of people watching just 1 week in the whole semester.
If you set K equals to 10, you should get 10 clusters that fit very well, saying these people just watched 1 week, these people just watched the other week, these people watched the next week.
But not one cluster of all the people that I watched.
Oh yeah, that's right. So what what you're getting at is that there's a different feature here. Not did you watch in week 1 or week 2 or week 3, but did you watch in a single week?
Yeah.
And that gets into the whole area of kind of feature engineering and how do you determine. So in here, in this example.
That may be that radial clustering thing, or
I don't know how it would work with if your feature is not in here, but there's some other relationship. So you have 10 people watched in week 0, 10 that watched just in 1, 10 that just watched in 2. And so here the feature is almost like an n-grams kind of thing.
You don't need to do it yourselves. You will add new columns saying watch ever, total counts of watches, let's say, or something like that, or ever watch at least one, yes or no, or whatever. And then the thing is, because now you have 18 features, week 7 from 0 to 17 and 18, that one is not so important. So you will need to put a bigger weight on that feature. So the differences between yes or no in that feature are way more important than, let's say, in a week 1, something like that. But it's a bit more complicated.
I think it shows one of the challenges in people often say, well, let's just have the data tell us what's there. In fact, I often say, let's just see what the data says is there. But there is why. What are we using as the data? And why have we choreographed it the way we have? And so intuition often drives. I mean, this was the intuition I used to align this data, but there's also a lot of theory that we could use to drive that as well. And so if you think it's total amount of activity or activity within a 24-hour period or so forth, that changes what these attributes, what these features will be in your model. And then you cluster based on those. Vitomir brought up a really important point, though, is that in normal k-means, when you do it this way, all of the attributes are equally weighted, and so they're equally used. Now, in the 2 space, that seems pretty obvious, but you could say, well, I care more about the y distance than I care about the x distance, and then when you get into this 18-point space, you can imagine wanting to say that as well. So there can be a lot of exploration of your data, trying to look at different clusters and different ways of engineering your features to give you insight into how that data is going to. But you're right, Weka would not be, this approach would not tell you that there was this sort of hidden attribute in your data.
So just follow up on that one, then given uncertainty of the number of clusters, when we do unsupervised, I'm coming from a management background and we do a lot of latent class modeling, so I try to see the connection and similarity between these two. So can you then actually do a methodological cross validation so that maybe the clustering solution that that you get from Kagan's approach, and then compare that with more a model-based solution, using more latent sort of class modeling type. Yeah. Because, for example, I was looking for some, when I asked a question about the model fit, actually it doesn't provide a model fit because it's not model-based. That's where I was confused. I needed to that. So can we do a validation to see a 5 clustering solution, for example, and then you approach it, you use a similar approach, similar approach and see whether.
Well, if you already have a model for your data, if you already expect the data is going to kind of fall into these different groups, you're not really looking for clusters in your data. You're more doing this classification. But there are techniques that try and that tell you the number of clusters based on some kind of fit in that. So EM is one of those, expectation maximization, which is the default in WECA, can actually tell you what it thinks how many clusters that you can have. And so there's a bunch of different methods that will do that.
And so in some research that I've done, I had the same temptation, which is to try to optimize something. Right? It's unsupervised clustering, but still, can we have a quantitative measure? Is this doing better? So one way is to have a target that you're trying to predict, do clustering, and at each k, do a cross-validation within the population of k, trying to predict that target, and see which k gives you the best cross-validated RMSE, or whatever the thing is that you're trying to optimize. There's also ensemble methods, which Chris will talk about briefly, where instead of just picking some holy k that is the answer, instead use a variety of different k's and ensemble the predictions that the different k models create together. Right. So then you're really incorporating all the different types of partitionings of your data. And you can easily imagine that there's not just one partitioning, right? A partitioning of k equals 2 could partition based on gender, right? A partitioning of k equals 3 could partition based on learning styles, or some other non-controversial type of categorization of students. But, so you can easily imagine that you might want to incorporate multiple k's, and that there isn't a ground truth k necessarily.
But in such a case, in that case, gender probably will have to be covariate, right? Because in this case, we're not. That's hidden. I think that's what we're not. Whether or not we can discover those hidden latent traits.
So,
which is an issue in re-identification of data.
I think it also comes down to the phenomena you're measuring, and as Zach kind of alluded to at the end, you may be measuring different phenomena with the same kind of clustering, the same attributes. You may be measuring. So let's say you throw in hair color and you throw in gender and you change k. You could actually see a nice split at 2, a nice split at 3, and a nice split at 5 with the kind of combination of 2 genders and 3 hair colors. So it really depends on the phenomena that you're expecting those attributes to speak to.
Could you give us an example of what could happen between the seed size?
Sure. Yeah. The seed, don't think of the seed as a size, think of it as just a random number. And so my guess is nothing will happen. But let's, this will be the one. Let's look for iterations 4. And so if we change the seed to some other random number, run this again. Now it took longer to come to some convergence, and these may or may not be the same category, or actual clusters. What's the error? Yeah, so here it actually found a different set of clusters that are fit. Yes. So if you jump back and forth, you can see what the differences are. It's important to note, though, that what you might label this first cluster, so or this second cluster here, let's call it, these are the people who watch all the time, might not show up as cluster 0 in the second model, but might be cluster 3 or something like that. But it actually looks like it was cluster 0 in that one. And so here you could just, you can scroll down this time. But here you can see like how many clusters you have. So you've got 6, 19, 55, 10, and 10. And here it was a slightly different setup. So normally you would run these many iterations and find the best. What I would say here is that the first run we did, given that the squared errors is higher, actually found got stuck in a local maximum and found a less optimal solution.
Is there a criteria to choose the set number?
Sorry, so this
a criteria to choose the appropriate set number?
There isn't. Yeah, so you would choose many different and then average those results. And I would do that programmatically. So when in this kind of data I ran it 500, 1,000 times. And I honestly don't know. That's just how much time you have and how big is your data, I think.
So essentially what you do, you run the cluster, the same clustering algorithm with the different seeds or whatever, 100 times, for each point, now you have 100 signers. Cluster 1, cluster 1, cluster 1, then maybe one's cluster 2, and so on. And you say for each point, you just take the most frequent. So this point was 99% of the time cluster 1, you say it's cluster 1. And then you average the point. And the thing, so now we've had two different results. When you have data that's hard to separate, you're going to have that. If you have really clear clusters, clear, empty space between them, whatever you choose as a starting point, eventually they will find the same thing because it's easy. The problem is hard.
And I think the schedule says we break at 3:30, right? For coffee? Does anybody know? I'm going to assume that's right because that's what I wrote down, which often isn't right. But yeah, 3 o'clock we break.
3 o'clock we will resume at 3:30.
Okay. Okay. Good to know. Okay, so I'm just going to touch a little bit on this and then jump a little bit into classification because Zach has some really nice stuff to show at the very end, and I want to make sure we've left time for that. Okay, so what clusters do we think might exist in the data? So you can experiment with k equals 2, with k equals 4, try the different data sets, see what's there, and see how that might fit the hypotheses that you walk into with this. And just, think about what this data means as you as an educational researcher. What do you think should exist in that data? The other question is, where do we think we might find an elbow? And that's the maximum number of useful clusters as we've kind of been discussing it. And so here I plotted, and I think I just used the default seed equals 10, so you should be able to totally replicate this. I plotted what was the error, how many clusters, and the error divided by the number of clusters. And here's what the Excel plot. It's not clear. The elbow method is not, the perfect method to do this. This goes back to we may be measuring multiple phenomena. Phenomena may be very noisy or ill-fitted. We might not have the right number of attributes. Should we choose 3? Should we choose 4? I'm not sure. And this is where we might lean on educational theory to try and give us some insight and then increase our ends and replicate. So replication, I think, is something that in learning analytics research thus far is been underutilized and is starting to become more and more important as we have more and more public data sets. Replication, I think, will be almost required for publication. Okay, so it's going to be coffee, but not yet. Hold on, 20 minutes. I want to jump in straight into the classification bit. So what if we want to predict which cluster a learner will be in based on the data that we have on them? And this is generally done in a supervised manner where the machine learning algorithm is given some training data and attempts to find rules to describe that data and thus fit people. So here you're looking to try and more understand the rules that might exist in the system. There's many different supervised or kind of similar approach methods. Logistic regression, I should say logistic regression is a common method used to predict categories. Linear regression, which is very similar, is a common method used to try and predict grades and fit lines. In this tutorial, I want to introduce one called C4.5, and in Weka, their implementation of it is called J48. And it all sounds very technical and nice, and you can drop sites and papers, but it's decision trees, essentially. And so here's an example. So the algorithm attempts to bisect the instance space. So you have a whole bunch of students and all of the things about the students. You have 5 different classes that you know exist. Somebody has said, yes, this student is in this class, this student is in this class, this student is in this class, and these classes are some kind of string label. So that's your training data. And what the algorithm tries to do is to bisect the instance space and recursively work on each portion. And to bisect it based on the attributes that give the most information about the ties to those classes. The algorithm stops when each instance in the instance space is of the same class. And there's various pruning techniques to make it harder to understand, but a little more accurate that are used. And so actually in the second MOOC on this topic, Ian Witten provides, he shows a visualization tool that I didn't even know existed in Weka that shows how this works. And it's really worth kind of a consideration to watch this instance space get bisected. But the end result is a decision tree of rules. And a lot of people don't use this approach. They use Bayesian approaches, or they might use support vector machines. The thing I like about this approach is that it's very easy to understand the rules at the end. And it's very easy to explain to instructors, to instructional designers, to theorists that are looking to tie that back to kind of what they know about the rest of the learning process. So here's what the rules might look like. If your ethnic background is 2, it's a very computer science view of ethnic background, right? It's just a number. If your distance from campus is close, if you're wanting to transfer college is 1, and your high school admission average is less than or equal to 91, then you will be a weak performer. If all of these things here are true, and your high school admission average is between 91 and 93, you'll be a moderate performer. And if your high school average is greater than 93, as well as all these things, then you'll be a strong performer. If your distance from campus is far, if your high school admission average is less than or equal to 85, you'll be a weak performer. Otherwise, you'll be a strong performer, and so forth. And so you can build these rules up. And actually, these decision trees get big quickly and get confusing quickly. And similar to clusters, everybody who falls into the leaf of the decision tree isn't... it's a little different from clusters, actually. I should take that back. But everybody, when you apply these rules to a data set, there is error. There are misclassifications. People, you've said, are weak performers based on some rules, a path in the decision tree, and that turns out not to be true. They turn out to be strong performers and surprise you and reduce your chances of publishing. So J48 is really about predicting categories, not continuous values like linear regression. I won't talk much about regression, but I think a lot of ed statisticians and psychometricians come from using linear regression as a technique. And this one predicts categories. So actually, that's an interesting question. How many people are from US universities? Just a hands up. So I'm not from the US university, but I'm now at one. And I don't actually know. I used to think that the grades that people achieved were continuous values, so linear regression made sense. But now that I'm at a US university, I'm not sure. Because they're like A, B, C, and what's a half an A or a little bit less. And it's unclear to me. And then this caused kind of a little life crisis as I was chatting with a friend about this. Well, really, when we give results in our tests, we actually have 1, 2, 3, 4, up to 100. That's pretty fine grained. And we can give people 0.5%, but eventually there's a round-off error somewhere, and the computer can't store any more digits. So aren't they all just categories? And it was a really kind of metaphysical discussion about what are numbers and continuous values. Anyway, J48 predicts categories. It seems to work really well for US grade letters. That's what I wanted to get across with that story. It's relatively fast and it's easy to read rules. It's not always clear how to interpret the classifications. There's multiple ways of being wrong, which is important to note. Sometimes you can be, you can have true positives, false positives, false negatives, and true negatives. So to say whether this person will be a strong performer or a weak performer, it might be worse to depend on your domain to guess that everybody's a strong performer and say, hey, you're all doing great, and it just increases their confidence, even though they're actually a weak performer. If you told them, hey, you guys, well, this wouldn't be a very good pedagogical interpretation, but hey, you guys all need so much more work, you're really hopeless. Then they might all just want to quit regardless, right? So when you have two classifications, it certainly matters. Whether you're right or wrong is a more nuanced question. It's how you're right and how you're wrong. When you start to have n classifications, that becomes even harder. So if you say, I predict you'll get an A, and you actually get a D, that's pretty crappy. That's not good at all. If you predict they're going to get an A and they get a B plus, that's just, it's not great, but it's maybe not the end of the world. So how you're wrong really matters in some ways.
There is this big example of cancer. So if you say you don't have a cancer, and the guy has the cancer, it's waivers and saying, oh, you have it, and you do later on do a follow-up analysis, say you don't have it. It's much cheaper to run additional tests than to say you don't have it. That, not detecting it is waivers than detecting it.
And this is a place I think the learning sciences has a lot of opportunity to inform computer scientists who are building some of these models, because they're not always sure what it means to be wrong. When I'm wrong, how bad is that, and what should we do on that? So there's a design in between the prediction and the results of the prediction. But single numbers are really nice, actually, at the same time. And there is a fairly nice measure of accuracy called kappa, Cohen's kappa, or Fleiss's kappa. Fleiss's kappa is what we'll use. People who have done inter-rater reliability studies, this is the exact same measure. It's a value between, negative whatever and 1, where 0 is just a chance. I flipped a coin if it's an evenly distributed binary value. And 1 is a perfect value, right? So you have the 0 to 1 scale, where 0 is chance. This is actually a great thing to think about as well when you're looking at products that are doing learning analytics. So there is one vendor out there, and I'll protect them by not saying who they are. But they talk about how great their predictive accuracy product is, and they can predict who's going to pass a course with a 94% accuracy. And that sounds great, but don't roughly 94% of people pass a course? I mean, in university, we don't, it depends what university you come from and so forth. But if I just guess everybody's going to pass a course, I'm going to get a 94% accuracy, I think. So you don't have to have a lot of special sauce to be able to do that. However, that's a kappa of 0. So that's not a very exciting kappa. Zach, did you have something?
No, starting the next.
I would say on the kappas, especially if you're looking at building models from data that you actually have to train with and so forth. I've always said you can have big kappas and be reliably wrong all day long. But it's not necessarily a measure of accuracy as much as really strong reliability. And you still have to do the validation work to ensure that it's accurate.
Sure, yeah. Yeah, that might be so I think, well, I mean, there's other issues with kappa, and one of them with kappa is that I don't know how good is good enough. Right. And that's an ongoing struggle that I have in my own practice as I'm trying to build predictive models. So I built a predictive model for a MOOC. On day 1, how well will the student pass or fail the class? And the result was a 0.2 kappa. That's how good my MOOC was, or my predictive model was. Is that good enough? Like, what can I do with that? And so it's a little unclear. How high do I have to get before I can start showing that to students? And I think that's a real challenge in using kappa, and that's something I haven't seen any real work on in the learning analytics literature. Is what are the effect sizes that you need with kappa? And in fact, a lot of the sites that go back, there's a very popular one. I don't know why I can't remember the name of it, that breaks kappa into these kind of strata that says, a 0.8 to a 1 is excellent, a 0.6 to a 0.79 is good, and so forth. And in their paper they say, and these were totally arbitrary, we just choose these. They seem kind of reasonable. And they have like 1 billion sites to this, and it's totally unclear. And I think that's where the learning sciences can help try and help us measure the impact of how predictive our models need to be, and in which way do they need to be predictive.
One thing, it depends for what. So if you are showing the student, if you nudge B+ student, so A class student when they get A to learn a bit more, it's not a big hard. You can use kappa 0.2. I mean, whatever kappa is, if you're showing some suggestions rather than nothing. But if you're gonna put patients to a certain condition or something, then you need to have way bigger kappa. So that's why it depends. You can't. That's why you never have a research that says everything below 0.5 is bad, because it's not.
Right.
Just besides kappa, I think the reliability issues in classification or any classification sort of focus, I think, has been an issue because traditional reliability doesn't apply to classification context. So what was done was actually people tried to sort of simulate data and then kind of again knowing the true parameter values, meaning where people actually will be classified into, and then you calculate the actual cutoff based on that empirical versus true values. And so there is some work actually that has been published using this.
So, but for reliability, you're just looking for overtraining, essentially, right? I mean, this is what you're...
So what people are arguing is actually the traditional notion of reliability cannot be exactly applied to classification context. So the meaning of reliability, or what we have to be concerned about in this kind of work, has to be more the classification accuracy. So then how do we determine, or is there any way to calculate that classification accuracy? And one way of doing that is actually use sort of set of true. Some work has been done.
It can be surprising as well as some work that students are presenting at the Vision Knowledge Tracing Workshop at EDM, where metrics that we've relied on for a long time, like AUC or A prime, to be the goodness metric to say how accurate is this model at portraying the real world. When you do a simulation study, those end up to not be correlated at all with the ground truth parameters. Instead, it ends up being precision or recall or log likelihood. So picking your error metrics is very important. So I like the conversation that's going on right now, and I'm not going to hold us up very much, but I just wanted to show something that Chris was alluding to, which is what are some of these examples, mostly toy examples, that would break k-means. So expectation maximization, clusters based on Gaussians, k-means, clusters based on spherical Gaussians. So here's an example where you have two features, say the x and the y-axis. We just have this two-dimensional space, and clearly there's not clumps, right? This is not something that k-means would handle very well, but it's something that Spectral does handle well. So let's say we did want to do k-means clustering on this. This is k-means with a k of 1. With a k of 2, it's split the circles in half. And the upper half has become one cluster and the lower half has become the other. And you can imagine the centroid is probably somewhere in that second inner radial. You can k equals 3, it's split into 3 pizza pies, pizza slices, 4, same thing, 5. So accuracy-wise, maybe k equals 5. You might find an elbow, you might find a best k in terms of whatever your entropy or silhouette method is, but it's really not representing the distribution of your data.
Then I think you need to go back and look at the features that you select because of this result.
Go back to the features.
This means that the features are not representable enough to show
Or the
these are clusters.
distance measure.
Right. You could use like a different distance measure to try and address that, or features actually. So you could pre-process the data and look at their distance from some kind of center, from some origin metric, and rebuild your features. But I think Zach's going to suggest that you could use this other method for clustering as well.
You can use the other method. Eyeing your data when it's two-dimensional is pretty easy. When it becomes n-dimensional, it becomes very difficult. You can use some factorization techniques to try to handle that.
I think the best way to do that is exactly as you mentioned, is to go to different techniques and see all of the results of these clustering and try to see, get a sense of how the output of this one fits the theory or not. Because the machine is trying to cluster with a different perspective than the human is interpreting the data, right?
That's right. The fit can be a difficult item to find. So if you don't have a target that you're progressing to, or a class. So you can imagine what's going to happen here. Here's the k equals 1 spectral. You still need to define the number of clusters it's fine. So I'll do that automatically. K equals 2, 3, and here's the magic 4. If you go farther, it will split rings. So spectral is based on the spectra of graphs, so it's a graph theoretic way of clustering. If you want a really nice software package for doing this, that's for MATLAB. Sorry, I don't have the link posted, but just type in spectral clustering as one word, 1.1. And there's a great team out of National Taiwan University that has an open source package that works in OS X and Linux. And it does a great job. So, let's see. We got 4 minutes. So, as I said, it's based on the spectra of graphs, and what it does is it represents each data point, where the data point is a row in n-dimensional space. So think of a point in n-dimensional space where your n dimensions are the number of features you have. And then it calculates the distance between each point and the other. So it creates this square matrix called distance matrix. Creates a distance matrix, and then does some nice statistics on that matrix to make it Laplacian, which gives it some good properties. And then it does eigendecomposition on that distance matrix. So basically it's looking for the vectors that most describe the properties of the graph, its vertices and its edges and the distance between nodes. And then essentially what the graph clustering does is it does an approximation of the normalized cut. So getting a little CSV here, I apologize. But basically what it wants to do is it wants to maximize the volume of the partitions that's creating, while at the same time minimizing the number of edges that get cut. And that's called the normalized cut, but it's not tractable to do in practice. So graph clustering is an approximation of that. So practically speaking, when would you ever expect for something in the real world to manifest itself as a connected grouping rather than a clumping? And the example that I think of is, let's say you're doing cohort formation in a MOOC, right? You could, let's say you want to break people out into 1,000 student groups. You want to break them out based on a hypothesis that the attributes of the student, be it level of education or age or gender or whatever, should lead to better communication, better socialization, and better learning. If you cluster them based on k-means, you'd be clustering based on this centroid, this prototype idea that these people are somewhat similar to this average of them all. Whereas if you clustered based on spectral clustering, you would make sure that everybody had someone they were very similar to that's in a group, right? So I might not be similar to this person, but I'm similar to someone right next to me who's similar to someone right next to her, et cetera, et cetera. So you're all connected through each other. That's a hypothesis for one way of grouping people that might be it. That's all I have.
Yeah, I think that's a great place to break. And when we come back, we'll finish classification and do some hands-on classification, and then do a little MOOC data talk. Yeah. I mean, you could create attributes to try and describe that. No, I really like it. What do you think of that? Yeah, that's a good thing. Yeah.
No offense to you. Oh, it's right. It's pretty much next one. No problem.